Welcome for another developer meeting. First of all, Christian will not be able to make it today. He excused himself because he had some family issues and he had to support people from his family. So on the Sunday today, he's not able to make it. Just for a short update, he's still working on the project management setup and the definition of the work chunks. This is, I thought so. It would not be possible to do this in 2 weeks. So maybe it will take him another 2 weeks. Well, let's see. So, because this is a developer meeting, I also want to give you an idea of what happened that you're not aware of, which we do not promote in the Discord yet, but things that are going on, let's say, behind the scenes, things we are preparing to. And then I will shortly talk about the team building thing. And then we step into Paul's ML and Paul and Mike's ML approaches, and let's discuss this for the rest of the meeting. So, for this purpose, excuse me, this is that one. I will share my screen, and I hope that it will be shared, because I had some issues with sharing and recording at the same time. So, okay. Do you see what I see? The enclosure?
Yeah.
Yeah, okay. So the enclosure is in production right now and will be finalized by after the first week of December. And we are right now setting up our Amazon store for this. This is quite a procedure, but we hope to manage it by the end of next week. So everything should be available by, let's say, mid of December. So that's the one thing. Oh, it's an empty one. The other thing is we let design by The Signal. Some people know about him. It's Dan from the UK. He did a lot of mission patches for other organizations like ours. Let's say for Jeremy McGowan's Osiris, he did it. And he's now working on a design for Sky 360. And this is, let's say, in the middle of the design process, a stage of our mission patch. What's still missing here is the front part where the station will be placed, and the text will be in another font, of course, and it will be, let's say, more golden in style. We want to use this design not only as a patch, a mission patch, but also as a design, let's say a basic design for our merch on Patreon and wherever we do our kind of merch stuff. So that's just for this update. I can put them away. So the other thing that is we are working hard on replacement for the Dahua security cams because they are not available anymore, and the few pieces that are still available online are, let's say, very expensive. So I stop sharing now. Okay.
Yeah, I can see.
Yeah. So we knew we had to replace this Dahua security cam as fast as possible, and we are now in testing some components. We tested some optics yet. We are getting more optics in right now, and we need to focus on our necessary specifications, but also keeping the price as low as possible. So we are now sitting around between 400 and 430 euros, which makes it $450, $460 kind of. This camera, this new all-sky camera, will be available, we hope, within the next 2 weeks. So after the, let's say with mid-December. There's still some optics to be tested, but I think we can make this time by mid-December and put it in our new Amazon store so people can finally get new fisheye cameras. Yeah, that's, let's say, major things that's going on in behind, where we still work on all this setup for procurement from products that is needed, from the enclosure and all the add-ons that are needed, and the old SkyCam, and we're still working on the PTZ. Bojan is now finished with the Slipring, which is a component that is, because the PTZ camera is a 360 endless panning head, so all signals and cables and power that run through have to be on a slip ring, so that have all this connection and always any way how fast, how much it turns horizontally, that we do not have a cable knot or problems with cabling, let's say. So a slip ring is the way to do it, and he's working on a new slip ring that he designed for us for Sky 360, so that we can have it on a much cheaper costs. The normal slip rings, for example, we use power and Ethernet to channel through the slip ring. Devices like this cost around $300, and we focus more on the $30. So we will get our own slip ring for 10% of the normal costs. So these are.
Is that something that's machined?
It's basically a PCB. It's two PCBs. It's two circular PCBs sitting on top of each other, and between those,
Oh, I see.
you've got those. I do have a screen. Wait a sec. Hold on. I can show you a picture. I can share. Oh yeah. There it is. Yeah, let's say something like this. And I have to share the screen again. Where's my screen? No, it's not shared. Okay, now I share that and that. Do you see the slip ring?
Not yet.
Not yet? Oh dear, this sharing is not really working. Do you see it now? No. Brett, do you see the slip ring?
Yeah, there it is.
There it is. Okay. So that's two sheets of PCBs with pins, roller pins, and these rings. So there's a connection coming from underneath. It's on these Ethernet and the power lines, and this is the stator. This is the button part is the static part, and the top one is the rotating part. And these are the rings that run around in circular. So all these pins coming from underneath have always a full connection, so that we can pick up the signals and power without breaking any interruptions. Let's say this is a top view, this is a better view. This is a cross view, maybe this is more interesting. Do you see the cross-section view?
Mm-hmm.
Okay, so that's a cross-section view, let's say, of this slip ring. Yeah. Did this answer your question, Mike? Mikey?
No, it answered my question. That's what you're asking.
Oh, sorry. Okay, excuse me. Does this answer your question?
Yeah.
Okay, fine. So, okay, next thing is, before we start into machine learning, I just want to stop shortly on what we thought are, I have to share this screen. Oh dear. I always have to switch between sharing and switching. Do you see the teams now?
Yes.
Okay, great. So these are the let's say the main components that we have to develop, hard and software. And the idea is to define teams where each team and people work in these teams have an overview who is where and who is doing what. So basically we have, let's say, 6 teams. The master control program is Christian and PPTip. Christian was talking with PPTip. I don't know his full name. I just know him by his tag. He's, sorry to say, not here today, so that we can go in details. But Christian is in contact with him, so they are the two of them who set up the master control program. They're also doing the INDI stuff, which is just adjusting the INDI libraries to our external devices that we're using. Kristen is implementing then his image processing stuff, so that to Paul's team, Paul and Mike's team, the stream is pre-processed and ready to be machine interfered, neural network AI interfered. Don't know how to say this. If I sound stupid with AI, please don't get me wrong. AI is totally something new to me, so please bear in mind. Please bear with me. So if I talk about AI, take it with a grain of salt.
But that's an inference.
Inference.
Not an interfere.
Inference. Okay, thank you. So Chris and Mia were both working on the All Sky Cam as the hardware, because we are now testing some kind of optics. We are now focused on a sensor, the IMX266 sensor, which has 12 megapixels. Is a Starvis sensor with the good range from the 300 to the 1100 nanometers. And we hope to have it, let's say, available in about 2 weeks. But still a couple of days left for testing kind of some optics. The PTZ cam is a work in progress since half a year now. We are pretty much done with the design. Hardware-wise, these 4 people are working on the hardware. Oops, sorry, I cannot. Can you see my mouse moving over here when I move over the hardware?
Mm-hmm.
Okay. So these are the 4 people working on the hardware stuff. And there's still a question mark on Paul, Mike, and Chris, whether the ML inference layer is, I would not say it's the same, but maybe adjustable for the PTZ cam. Maybe, and maybe you guys can do this also in the future. But for now, we focus on the All Sky cam because this is the core element. Let's say the master controllable cam and the All Sky cam are the core components that we have to solve until we can say that we have, let's say, a beta system that's working. And then from there, we can add on another stuff like a fancy GUI and the PTZ cam and so forth. All right. So stop sharing. Right on. Okay, that's a short update for what's going on besides software development. And I would say, Paul, can you maybe run us down with your experiences from the last couple of days, things that you even posted in Discord?
Sure. Thanks for that. Can I just check that we're recording? I'm not seeing anything that's showing.
We are recording.
Showing the record. Okay, thanks. Okay, so before we sort of get into what I've done, I want to make sure that we reset expectations. I noticed you asked for an image for the Nano. So we're nowhere near being able to produce an image for the Nano at this point.
Yeah.
So the best bet for that is probably going to be taking the simple tracker and seeing if we're capable of running even that on the Nano, and that's a direction that Mike's taking at the moment. So he's trying to figure out some of the hardware capabilities of it. Mm-hmm. So on the ML side of it, essentially what I've done is sort of taught myself how to build ML models. And in that process, I've learned quite a lot. I've still got a long way to go, but I've learned quite a lot and come up with some initial results. So I started off, as Chris suggested, with the RCNN model, and ran that. Now the RCNN model is a very large model and takes a long time to process things. So when I say talking long time, I'm saying like 5 seconds on my laptop to process an image. So
image.
this is unlikely per image, right? And this is on a laptop, and my laptop, for everything I've seen so far, seems to be faster than the Nano, even using the GPU capabilities of the Nano as well. So this is not something that's going to be deployed on the Nano. However, firstly, it's helping me to understand how to train one of these models, and giving me the confidence that yes, this is doable, right? I'm using what's probably the best model for the job.
Yeah.
Now, the challenge is to do the same thing, or I'm going to finish tuning this one, and then do the same thing for a model that's more capable of running on lower spec hardware. One of the other things that we could get out of this is we can use that RCNN model to auto-label our other stuff. So it's kind of like bootstrapping. So we're using the simple tracker to label input to the RCNN model.
Okay.
And then we can use the RCNN model to auto-label much better than the simple tracker can for the next iteration. So that we don't have to get a whole bunch of human labelers doing this. We can sort of bootstrap ourselves off of the simple tracker and then the RCNN, which looks like it may be plausible, which would be fantastic, because then I can get a lot of training data to use with a future model. At the moment, I'm kind of hand creating this data, and the question is, do we build something that allows other people to hand create this data, or is that a waste of time? And can we get the RCNN to a good enough place where it can auto-label?
Yeah, okay. When you say auto-label, so you have a pre-labeling by the simple tracker, and then you refine this with the next inference layer. That's what you mean with
Yes.
Okay.
Yeah, so the simple tracker is outputting a bunch of labels, but it's also picking up planes, it's picking up birds, it's also picking up a lot of clouds. So I'm going in there and taking out the clouds, and then feeding the moving objects into the RCNN. And then if I can get the RCNN to a good place, it'll be much better at removing the clouds. And then I can use that to auto-label a much larger set that I would then use to train the RCNN again, which would make it even better, which I could then use to auto-label the entire set, in which case I've got a really good data set to feed in to what's less sophisticated model, but should have more data.
Okay.
Which hopefully we can run on the Nano. I mean, very hopefully.
That's quite neat. If you can get that to work, then I think that's really, that's really kind of cool. That would be awesome, because it kind of then just essentially it's helping us move along almost by itself. I really like that idea, actually.
Cool. So the best I've got so far, and it's literally just this morning whilst we were starting the meeting. If you go and check the machine learning channel, I'm not sure if you can bring up the picture in the machine learning channel.
Oh yeah.
So this is kind of where I am at the moment.
That's a bird in the plane, right?
That's right. If you can just bring up Could you
Some
bring
leaf
up
in a
this on
plane.
screen share?
You can click by yourself. I record this and it's in the record.
How do I do this? Sorry, I'm not very familiar with this whole thing.
It's more easy if you click yourself in our channel and click on the picture.
Okay. All right.
Everyone sees it now. Okay.
Okay, good. So the green box is where it's supposed to be. So this is an image that it hasn't seen before. It hasn't seen anything like this before.
Okay.
The green box is a plane where it's supposed to be, where I'm hoping for it to find. But what it's actually picked up is a bird that was only in the view for that frame. And this is from a picture that's 2,000 pixels by 2,000 pixels. And I've zoomed in on that particular picture. So it's actually a very small object compared to the rest of the image. And the bird flew across, and it registered probably 5 or 6 frames across the entire SkyCam. And so it's great that it's picking up something that fast. It's not as good that it didn't pick up the plane. Now the plane is a very relatively slow-moving object because it's up at probably 30,000-ish feet.
And less contrast.
Less contrast. There's clouds cover there as well, and it seems to be sort of similar color to the clouds. So that is a very difficult object for it to find, but hopefully we'll get there. One of the challenges I'm having is usually before feeding one of these images to the neural net, they're resized down to a much lower resolution, which is how some of these
the whole picture, the whole frame downsized.
The whole frame is downsized, so they're usually fed in.
Wouldn't you lose a lot of information by downsizing?
Exactly, that's the problem.
Why could you crop it? Why not crop it?
Because I don't know where to crop, right? We're trying to find it. It's kind of a catch-22, right? I don't know where to crop to.
Yeah, okay, but you have the simple tracker that gets the first crops, the first bounding boxes. Maybe it's a stupid question. My idea is if you find a bounding box and you don't know what is inside the bounding box because you only know there's motion, there's significant motion, let's say, and just draw a bounding box and crop a new image out of that bounding box and pass that over to the ML.
So in operation, we wouldn't be able to run both the simple tracker and the neural net at the same time. And at the moment, we're not even able to run one of them, let alone 2 of them at the same time.
Okay.
So I think the way forward is to get the ML to a place where it can detect these things. The question is how performant it is. So what I'm doing at the moment is feeding in the almost original images. And that's why it's taking 5 seconds on a pretty fast laptop.
Yeah, I think one thing just to mention to Richard is that the size of the image obviously has a direct impact on how long it'll take to process. There's a direct relationship there between size of image and how long it takes to process the frame.
Yeah, the other thing is that these are not 3-dimensional images. They're not red, green, blue. They're red, green, blue for the optical and hue saturation value for the optical flow. So they're actually C60 images, so they're twice as large as a 2,000 square image, color image. So these are very large amounts of data that's going into the system, which is why it's taking 5 seconds.
So to understand this, the image, the frame that's coming in, is an RGB frame, right?
Yep.
Okay. But the optical flow is running on an HSV, also hue saturation value.
Yep.
So you have to transform the image. Every frame you have to transform before you go into optical flow.
Well, not quite. So if I get frame 1 into the system, I've just got the RGB values. Now I get frame 2,
Yeah.
and then I do the optical flow between frame 2 and frame 1, and the output from the optical flow algorithm is an HSV. So then I take the output of the optical flow and just concatenate it with the RGB values, and then feed that into the net.
Stupid question. Why is the output of the optical flow another image? I thought the output of the optical flow is vectors.
Yes, it is. That's what HSV. It's the direction and the magnitude. That's what the HSV represents.
Yeah, but is this just a list, let's say a text list
Yeah.
of vectors? I mean,
It's
just
numerical.
vectors?
It's a numerical. It's just a numerical array. You can just visualize it as
Yeah,
HSV.
Okay, but you do not have to visualize it.
No.
Yeah, okay, got it. I mean, this is information that you can pass on over to say where the areas of interesting optical flow takes place. So from
that
yeah.
Yeah, so that might be an option. Again, it's very difficult. I may be able to use the optical flow to pre-process the image down to smaller images. The challenge there is with things like that plane, it's moving at almost the same speed as the cloud. Mm-hmm. And it's probably not going to be able to distinguish them from the optical flow. So yeah, it's a possibility though.
I think the optical flow is geometrically based. It's not on the background based. So the question, when you move a picture of a picture in the view, the whole picture is moved because it's geometrically bound to the background, but not the image in the image. You know what I mean?
No, you lost me.
If this the plane moves, it moves because it moves, let's say, from coordinate xy to coordinate xyz, xy2, let's say. It's a geometric change, not relative to the background. It's a change within the geometry of the frame.
Right.
And then it should.
But then you could also use.
Yeah.
You could also use the argument that the cloud is moving in that way as well.
Yeah, both.
It's just a larger point.
Yeah.
But if the plane moves in a different direction than the cloud, then it's maybe still good information, no?
Yes, absolutely. So it kind of depends. It kind of depends on the scenario. So if the cloud's moving one way and the plane's going the other, that's a much stronger signal for the optical flow. Okay. So both going in the same direction, it's a little challenging.
Okay.
And with the clouds, I'm also wondering, with the optical flow, if you have like scattered points throughout the image that are not directly connected, that are moving, does this contain some information that this is probably clouds, like scattered points that are basically interpreted as objects, but they are moving all at the same speed in the same direction, and therefore it's very likely that this is a cloud actually.
Yes, maybe we're probably going to want. If there's anyone else that can help with that, that's probably not a good role, a good challenge for me.
I think Jannik, the thing is that if a huge cloud moves, you don't get optical flow above the whole cloud. You get it mostly concentrated on the edges, let's say, where there's distinct contrast. Within a cloud, it's only gray and gray. You don't see any contrast. So it's not optical flow applicable here. Not applicable, it's always. It doesn't create flow rates here because it's not decisible between two shades of very similar grays, you know. It's more reacting on edges.
On the edges.
Contrast, right.
Yeah.
But then again, it's a problem. You can't say, okay, if there's one cloud, one little sheep cloud, then you can circle it in and say, okay, that's a distinct thing that moves across the sky. But most times clouds are big and they fill, let's say, half of the view. So there's not movement recognized. Only movement of edges is recognized.
Yeah.
Yeah, Paul. Okay, go ahead. I have too many questions. Please go ahead.
So I'm going to put another image in the Discord channel to give you an idea. This is both the RGB and the HSV, so you'll see the optical flow for that particular image. So just give me a sec.
Yeah. While Paul is searching for this pic, I want to just talk about would it make sense if we apply optical flow and therefore we can find where movement takes place? Oh, there it is.
Yeah. Sorry, I can figure out how to do video and thing at the same time. Okay, so it should be in there.
Yeah, we see it.
Okay, so you can see, so on both of them I've drawn the bounding boxes. So you can see on the bird it's got a blue color. So color represents direction, and then the brightness of it represents speed. So you can see it's a different color and it's much brighter, which to the ML is a lot more obvious.
Hold on, you're talking about on the right side we see light blue stuff and white stuff. Is that what you mean?
Yeah.
And it's close to the red bounding boxes, for example.
Yes.
Okay.
Is that the optical flow? No, right?
Yes, it is.
Ah, okay. So that's similar to what I tried to say, I guess. So all the green stuff is basically just thrown out, right?
Yeah, if
Is that true? Because it all
yes.
has the same direction basically, and that tells us it's not something interesting. Like a
Yes. So and I'm not sure if it's always green. I don't think so.
yeah, I mean, if it goes to the other direction, but I mean, you have a large surface with the same color basically, and that means it's not interesting because, yeah.
I mean, I see what you're saying, and so if you could, I don't know what the mathematical term for it is, but group all the vectors that are aligned into one, and then identify vectors that are not aligned with that. There's probably some mathematical function that is pretty good at that, but I'm probably not the person to develop that. So yeah, that might be an interesting direction.
Yeah, I also don't know much about machine learning, so maybe I just thought about some kind of a pre-filter maybe that is helpful to get rid of the clouds, for example, because what I heard or read here in this Discord, it sounded like clouds are still
Yeah, you're talking
eventually
about
an issue.
stuff like background subtraction, but it's background subtraction is not very good for our cases because objects are very small because of distance, and you only have little specks. And background subtraction um, is more or less, I wouldn't say blurry, but it doesn't recognize very small things.
Yeah, but I mean right now it's about identifying larger surfaces in this right image here that have the same color and are therefore very likely not something that is interesting. It's moving,
Yeah.
but it's a larger surface, and therefore it's very unlikely that it's interesting to us.
Yeah. I would interpret what Paul said the same way. What you see in green is slow motion. What you see in
Right.
blue or white is high speed motion.
Yeah, right. And then, yeah. And maybe all the yellow stuff could be something interesting. So just as an idea.
This is a representation of the data is generated by the optical flow, and Paul is representing this by this color spectrum, let's say.
I know. Yeah.
Okay. So it depends how he defines the spectrum and what vectors are which colors or so. It's
Of course, yeah. This is just an example.
Yeah.
I'm just talking about this specific example. Let's say like differences in color and how much surface area the different colors have in each picture. I think that could be an interesting information in general to make distinction between something that is interesting and something that's not interesting.
Yeah, it helps to define the thresholds.
Yeah.
Okay.
But again, I'm not a machine learning guy, so it could be totally
me too, and
unhelpful.
that's important because if Paul can explain it to me or to you, then we also can be sure that whatever he says, other developers maybe can understand it as well. You know what I mean?
Yeah, for
so
sure.
The challenge is on Paul now. Okay, Paul, go ahead.
Yeah, so I do think there probably is some information there. I think the challenge would be making sure that so if, for example, you see where the plane is, it's kind of yellow. So if I zoomed in on yellow where that plane is using something like that, I'd also have to zoom in on yellow on all the other yellow patches, which would probably end up with more data than just taking the entire image and feeding it through the ML. So that's kind of the trade-off that
this yellow
you're
is
looking
a lighter
at.
Yellow, I'd say. So there is a distance between these two. I mean, the yellow next to the plane is a more saturated yellow. So there is a difference in threshold.
Yeah. And the thresholding is the problem with this approach, right? Anything that's manual and says, okay, let's put a threshold in. So, for example, the simple tracker has a threshold for what it decides is motion. And if you put the threshold too low, you get a bunch of clouds. And if you put the threshold too high, you miss all the small objects. So the ML approach is like throwing away all of that and saying, let's look at the image at the whole. Let's do the same things that humans do. Let's identify edges. Let's put edges together to identify objects. Let's look at movement. So I think that's probably the right approach. But as I say, the challenge is trying to figure out how to do it in a performant manner. So that's kind of where I am. Now, I have a lot of ML type questions for someone who's more experienced in ML than I am. But I don't think we have an expert here today.
Chris is not here. Chris from Houston isn't here.
No.
Yeah.
the things I'm trying to identify is what the loss metrics that I'm getting from the ML and the average precision and average recall, how to interpret them, and therefore what to do next. So I think there seems to be a lot of literature about classification optimization, but I'm having trouble finding much about object detection optimization, which is what we're doing here. So yeah, I know I'm not going to get an answer. Maybe if he sees this video at some point.
I think, I mean, to be fair, I think Chris did mention that on the call last or 2 weeks ago, where he also recognized that that was going to be the challenge. So, like everything in the world of machine learning is very much geared to classification, classifying objects versus being able to detect and not detect motion but not classify the object. I think you also recognize that as being quite a bit of a challenge, really.
Yeah, undoubtedly, and this is cutting edge research for a whole bunch of people at this time, right? We're just sort of moving. The challenge it seems to be moving from image classification to image detection, because image classification is somewhat of a solved problem now. Now the next hard thing to solve is object detection, and then you add on top of that a temporal dimension with a video, then that's even harder. And then you add on top of that small object detection. Well, that makes it even harder. So there's some very challenging parts here.
Paul, a question. Is it true that neural networks run faster on smaller data sets? Let's say, not small data sets, wrong word, on smaller resolution, frames with small resolution?
Yes.
Okay. Would it make sense if, let's say, we make a robust optical flow detector that finds, let's say, in this example, what you present here, for example, it finds not only two, let's say the plane and the bird, but maybe it finds 20 others. But let's say 18 of the others are edges from clouds or trees or whatever. So noise. But if this optical flow is working on any kind of situation via light, I mean in night as well, in blue sky and cloud and rain and what have you, if we can make a robust optical flow algorithm that extracts any kind of number of movements and draws bounding boxes, couldn't we then very quickly actually, or very easily, crop all, let's say that these 20 events that are detected with the optical flow, take these events and crop that out. Let's say the bird here is just 50 by 50 pixel, I would say, in a 2880 by 2880 frame.
Yeah.
So this would be just 50 by 50 pixel, and pass that over, and all frame by frame wise, pass that over to a neural network, because on the 50-50 pixel it must be very easy to detect anything, which is, let's say, a very high signal to noise ratio.
So that is interesting. There's some, and I think that's what Dahua was suggesting earlier. So there is some trade-off. You don't want to go too small because you lose context, right? Yeah. So as a human, if I gave you that blob of pixels, would you be able to know that that's something of interest? Yeah. So you don't want to go too small, but so maybe if we just chose the top 5 instead of the top 20, because ultimately it's the number of pixels that you feed in per frame. Right? So if you do 20, you'll be doing 20 times 50 times 50 versus 2000 by 2000 for the entire frame. So as long as the number that you're feeding in is probably an order of magnitude lower overall, then we might be somewhere near real time.
Yeah.
So yeah, I think that's an interesting direction. I could do with some help in analyzing the optical flow, because that's more of a mathematical
Mike,
thing,
wouldn't
and I
that
don't
be
know.
something that you could do? Mike, you there? So
I am just sorry.
just
Just say that again.
to crop out, to find with the optical flow, to find movement, build bounding boxes, let's say blob it to know they belong together and are not several movements by themselves, and then crop an image out and pass that over to Paul's algorithms.
So yeah, so I've got a couple of thoughts on that, and so my understanding with some of this ML stuff is that the images that you feed in all need to be the same size. I'm not sure if that was. I've been like starting to read up on this stuff, and one of the things I found was the image stream needs to all be the same size. So we would have to then define a size that would then be fed into the ML stuff.
So as I understand it, they need to be roughly the same size. So for example, the RCNN has like a minimum of, the default is a minimum of 800 and a maximum of 1300 on any dimension. So they have to be roughly the same size. I think the CNN helps with that. I think if it was just a fully connected network, you're right, it would have to be the same. They would all have to be the same size. But I think it's the ratio that you want to keep the same. You don't want to feed it squished in one dimension and then squished in the other dimension. It would have a hard time comparing those two. But as long as the ratio is somewhat okay.
Okay. No, that's cool. So that was the one thing. The other thing, so I kind of just want to also give you guys an update as to the direction I'm taking, I suppose, is the direction I'm at the moment is to try and get the simple tracker as performant as possible on a nano, trying to use as some of the hardware acceleration stuff. So that is to I kind of think so that's my next direct task, is to try and achieve that, is to try and see how performant I can get the simple tracker on the nano. So I know that the nano will natively support background subtraction. I also know the nano will not natively support deep optical flow. So I was going to kind of go down the route of trying to make it as performant as possible using background subtraction and see how fast I can get it to go.
Yeah, and I think that's a really important direction. I do think that's the highest priority next thing to do. So that it's basically understanding the hardware capabilities of the nano for the problem space that we're working in. So
so that was kind of my view as well, in all fairness.
Yeah, I think the analyzing like a pre-filter for the optical flow is a good idea. We've got some other things to work on first, I think. So we'll kind of circle back to that one.
Okay.
And maybe we can find someone that's better positioned to help us with more the mathematics on that. There may be an existing algorithm that does that. I just don't know what it is.
So also just to kind of just come back to your question, Richard. So as soon so I think the tracking algorithms work better when the frame rate is higher than lower, because obviously the object if we can process it 10 or 15 frames a second, the object that's moving, if it's a fast moving object, moves less distance across the frame, so it's easier for the algorithms to track. So yeah, it's very much geared to try, and once we can track an object, we can certainly, I think Paul's already done some of this anyway, is when we track objects, we dump images and also JSON files associated with those images, which give some context to the image. There's nothing saying that once we track a valid object, we can't crop that object and dump that as well as an image.
So I've actually done that on the single tracker. So there's a multiple object tracker. There's also a single object tracker that tracks them as single objects and dumps them as like a zoomed view of it.
Okay.
So you can play around with that as a starting point.
Yeah.
Okay.
I have another quick question, if I may. Have we rejected this YOLO v3 framework already? Are you aware of this?
YOLO was used with SkyHub, but we didn't come very far with it. The downside was that it has the image input has to be 800 by 800. At least Steve defined it that way, and it meant that we have to downsize a 2880 by 2880 stream to 800 by 800 pixels just to make YOLO working with it. And by this, we lose so much information. It doesn't make sense.
So I actually think I wouldn't rule out YOLO at this point, and there's other versions that have come since YOLO v3. It suffers from the same problem that RCNN does. Yeah. So RCNN should be more suitable for this problem because it's actually two neural networks, one to do region proposals and one to do regression and bounding box regression and classification. But the YOLO stuff should be faster because it's only a single neural network. You can feed, as far as I understand it, you can feed in larger images. It just has the same problem that it's much slower if you feed in larger images. So
I'm just reading that it's supposedly 1,000 times faster than RCNN and 100 times faster than fast RCNN, whatever that is.
Depends on the material.
Yeah. So
that was the reason why I'm mentioning it.
Yeah. So I'm using faster RCNN. But the YOLO's a perfectly valid possibility for something in the future. So I'd probably be looking. There's some other ones that are more geared towards mobile, so MobileNet, and the architecture underneath some of these things is actually pretty similar. So yeah.
Yeah, it's finding.
I think it's have to run them.
It's also finding something that works that leverages the Jetson's GPU capability. I always pull myself back to that in that we have a constraint on the hardware device that we are using, and it's trying to work within those constraints and being performant as well.
Yeah, it's much more than just the neural network itself. It's the pre-processing of the image to feed into the neural network that's very computationally intensive as well.
Yeah.
So, if we can offload that to hardware, it gives us a huge boost.
As far as I know from Christian, he has libraries for that astronomers are using, and he used it on the Nano as well, and they are very much performance-wise, and I think he did it on almost a 30 frames per second frame rate. But
Yeah,
it's
so,
what he told
so
me,
if
so he can give more details on
right,
this.
so if we're not feeding it to the neural network or writing it to disk, the current simple tracker does over 60 frames a second at 2000 square.
Okay.
So I don't think getting the data into the system is a problem. I think it's the processing that we need to do, which includes things like the optical flow, maybe background subtraction, and then of course feeding it to the network.
Okay.
Yeah, so I was I started thinking about this stuff, and I was wondering if there was some way that we could, when the Nano picks up an image, we can essentially pipe that through to like a Raspberry Pi that does some stuff to it. You know what I mean? So that, because I think there's going to be disk I/O issues if we have to start writing things to file and all this sort of stuff. And I was wondering if there was a simple way to, or an efficient way to get that image across to another device that can potentially help. So
Yeah.
the Nano is purely just there to process the images coming in, trying to find objects. It doesn't do anything, doesn't write to disk or anything along those lines.
Yeah, I think that's a good suggestion.
There's a product where you can stack up to 4 nanos on a stacker board. So you can have, let's say, 2 nanos working as one.
Okay.
But
Yeah.
At that point, I'd probably prefer an NX
yeah, probably on the long
because
way
it has
it's cheaper.
because it has the optical flow hardware
Does it?
and a much larger and more recent GPU.
Yeah. Yeah, if that is what it needs at the end, maybe we have really to skip the nano.
Yeah,
And
I certainly wouldn't suggest anyone get a Nano at this point.
yeah, we will need the nano for the PTZ anyways, but for the more problematic
No,
material on the fisheye, the NX would be more
the
appropriate.
the PTZ's not. If what from my understanding of what we're going to need to run on the PTZ,
Yeah.
I don't think the Nano is going to cut it there either.
It's a zoom scope, 40 times zoom. It should give you a very high signal to noise ratio. And we do not even have to have it on 2880 pixels, or let's say HD or 2K could be enough.
Okay, yeah, I mean we'll test this, but
Yeah, we're not there yet. Yeah. Okay, one question, Paul. You're working with a faster RCNN. What is the minimum size of an image, a frame, that can be passed over to the frame, to the faster RCNN?
you make it as small as you like. The problem is the smaller you make it, the less context it has. So with you as a human, so when you're talking about the ML, you should always thinking of it as how could I as a human understand this image? And if you've got a really tiny image, there won't be much context.
Mm-hmm. But let's say it's the same as with profile pics. I mean, in a profile pic, you see your face with a high signal to noise ratio because the rest, it's only 20%, which is background, let's say.
Mm-hmm.
And 100 by 100 pixels is enough for a human to recognize someone's face. I would just compare it to, as you said, to human view.
Yeah.
Let's say, is 100 by 100 pixel feasible for a faster RCNN? Is this doable?
I mean, technically, yes, you could give it that small an image. I just don't know how effective it would be. So it may work. It's like I don't know.
I think, yeah, so part of me also thinks there's probably some direction that needs to be, so with regards to this whole project, we probably need some ideas to what the end goal is. So if you track a dot going across the sky, is that a valid result? If that makes sense. Do you want to be able to track a dot and say that's a UAP, or do you want to be able to see something that's a bit bigger and say that's what understand what I mean?
So yeah, I'm just coming back to the system and what the system actually is. It comprises always something that runs 24/7 and scans a hemisphere. And then we always have a part that is doing a zoomed part of the sky. It's the same with opticals, what we'd use here with optical videos that are taken, and it's the same like with passive radar. So we scan the hemisphere 24/7, and whatever happens there has to be with a special device then be targeted and zoomed into. So let's stick to the optical side now. The fisheye is only there to recognize significant movement and to label it, let's say, and to say that is with high probability a plane and that is with high probability a bird and so forth. Because we need this in order, because there's not always one event, there are always a couple of events in one frame at the same time. So we have to know the difference. The difference has not to be that it has to be recognized as such. So, for example, this image that Paul posted, if you see the bird, you wouldn't say that's a bird if you have one frame. It could be anything. But it is a significant thing in the sky, and interesting enough to be followed up with a PTZ camera, for example. And because there are more events at the same time, we have to prioritize, because we have just one PTZ we can send to. I mean, we could have more, but let's stay with one for now. So we have to prioritize those events. Let's focus on the first event, which looks more like a UAP than anything else, for example, and prioritize that as number one. So the PTZ heads over, and let's say within a couple of seconds, maybe 10 seconds, we know this is a bird in the distance, or it's a drone, or it's something else, because we have a closed up view. And then the master control program can head the PTZ to the second priority item on the list, for example. So this is only interesting to separate the events by themselves. This pre-labeling, what the AI is doing on the fisheye, is only used for the prioritization of events to head over to the PTZ. It's not the final game here. It's only a pre-assessment and then prioritizing from the events and then heading over to the PTZ. And I think when we think in this direction, it makes things maybe a little bit more easier for recognition, because you do not necessarily have to detect everything. It could still be a very distant bird that is never recognized as a bird because it's just 2 pixels or 5 pixels. And the human would not recognize it as a bird. It's just there is something of high contrast. It changes shape. It moves there. It is there. It is from frame to frame. It is in the close proximity, so because it's moving and so forth. That is something we have to detect. Did this answer your question, Mike? Hello, is everyone there?
Yeah.
Okay.
Yeah. Sorry. I've just got. Yeah. It does, and yeah. It's I think it does. Yeah. Sorry, my phone's going. I just got to try and turn it off.
No
Give me
problem.
2 minutes. There we go.
Mike, we could even go that far that we say we do not need an ML at the fisheye. I mean, I'm just exaggerating now, yeah? Because we only need coordinates of events in the sky. And the only thing is how to define an event.
Yeah, so that's kind of, in all fairness, that's kind of what I was thinking. I think ultimately, so in an ideal world, what we want to do is at the fisheye, we want to go, right, there's something that's flying over, it's a bird, ignore. There's something that's flying over, it's a plane, ignore. There's something it's a leaf, ignore. Oh, there's something that's flying over, I don't know what that is. I need more information. Come on, PTZ, do your thing because we don't quite know what.
Yeah.
That's I fully understand that that's in an ideal world, that's what we want to achieve. I guess from a practical standpoint, and also with hardware constraints and stuff like that, and just being realistic, is if we have, it's just to try, I suppose, and achieve that. And if, yeah, sorry, I'm not entirely sure what point I'm trying to make, but it's I guess I understand from an ideal world what we're trying to achieve. I think we're just going to take it one step at a time and see if that is what we can achieve using what we have.
Yeah, Mike. At the moment, with you and Paul, we are discussing, let's say, the high-end version of the fisheye. That the software that runs on the fisheye material can really say, this is definitely a bird, this is definitely a plane, and this is this and that, and ignoring all that's not an event. That's the high goal for the fisheye. But let's say on the low end, we have just motion detection. Maybe we have, in this case, we got 120 motions, which would be difficult for the PTZ because it cannot follow 120 events at the same time. So in order to make this working, so we have not 120 events at the same time, we have to eliminate a lot of events until we have significant ones that are of interest. But this number, this short list, let's say 20 events that are interesting, if this is the second level of goodness, of functionality, it would be still important to be able to prioritize this, because even if it's a short list, it's too much for a PTZ to follow after. Because even if you have 5 planes, 1 drone, 20 birds, it's so much, and it happens often. I mean, when I look my material, I see this very often happening. I have 5 planes, 20 birds, in one view. It has to be prioritized somehow, because the PTZ would not be able to follow everything. Because we need some material on the PTZ to identify. The identification has really to take place. But in this case, we have a higher signal-to-noise ratio than on the fisheye.
I mean, currently we've got a limit where we will track 10 items using Simple Tracker. That's kind of our limit, because there is, and that's just, I think that's just an upper limit that we picked, so that can be changed. But there is a performance impact with, there is a relationship with the number of items being tracked as to how many frames per second you can process as well. So I think it's quite complicated, right? And that's, yeah, I guess I can't just come back to the point of that's one of the reasons I'm just trying to squeeze as much of a frame rate out of the Simple Tracker as we possibly can. Because then because if we can do that, then we can potentially look at tracking 20 or 30 items. I don't know if it will be able to do the classification of those. I don't know, but I think if we can track 20 or 30 items at the same time, personally, I would call that a win.
Yeah, absolutely, absolutely. This step is very much important, and also to create an image that we can roll out with an image for a nano, for an SD card. That would be great to have.
Yeah, no, I agree. I mean, yes, I I I completely agree with you.
Okay, Paul, last question to you. Are you in contact with Chris from Houston?
Not particularly, no. I've asked a few questions on the general channel, but I haven't had a response.
Okay. My question is, shall I make contact with him, or will you do it? I mean, I want to involve him a little bit more in our discussions. It's sad that he didn't show up today, but maybe we can, during the week, have a little conversation with him. What he thinks about some ideas we had today.
Yeah, I mean, that would be great. But I mean, I'll reach out to him, but
Okay,
we'll see.
you do that. Great. Okay, guys.
Um,
Anything?
so,
Yeah, sorry.
so
Go ahead.
let me just finish off that conversation.
Yeah.
I do think the simple tracker is probably our best bet for a version 1. I think, even for V1, we could set it so that the sensitivity is relatively high, so it won't get triggered by clouds, but it would get triggered by a bird flying relatively slowly at a sort of mid-level height, and it would get triggered by a low-flying prop plane, for example. But it probably wouldn't pick up those few pixel 40,000 feet planes or objects that are flying around. But that might be good enough for a V1, right? And then we can sort of start building out the deploy line so that we can deploy this to systems, and then start getting some more data as well. So, and I think in parallel with that, we try and get as good as we can on the ML side, and then hopefully we come up with something. At the moment, my best scenario for the ML side on the all sky cam is tracking movement. I think object identification is going to be extremely difficult. So discerning the difference between a plane and a bird is probably going to be beyond what I know is capable of on the ML at this point.
May I put a question?
Yep.
These neural networks are more or less working on image material. Could it also run on other material, let's say on data arrays?
Yes, I mean, I'd love radar data, for example.
Yeah, okay, yeah. Okay.
That could be a game changer.
My point is
We can feed
whether,
in radar data as well.
yeah, absolutely. And we will have this, and I'm discussing with some people who are very deep in this. Hope to bring them on in our team, but radar is still on our books. But if a neural network can also be used for data arrays, would it make sense to let it work on just the optical flow output? I mean, just on the vectors, and just like that, what you presented here as a representation of all the vectors in that frame.
Yeah.
Wouldn't that be sufficient to say, okay, we do not recognize it as a bird, to say this is a bird, this is an albatross, this is a falcon, whatever, but it behaves like a bird, you know what I mean? It moves like a bird. It moves.
Yeah.
Because we already know. Yeah, go ahead.
So that is interesting. I've kind of considered that. It is something I want to try. It's just not as high on my list as other things.
Yeah.
the reason that that's a bit of a challenge is because I do think it needs some of the optical data in order to make that. In order to discern that there's an object there. So often you'll look at the optical flow and there'll just be a big blob, and then you look at the optical and it's like, oh, there's a cloud. And it's just part of the normal cloud around it. I don't know why the optical flows even pick that up. Maybe it's a slightly lower cloud behind a higher cloud.
Yeah.
So without the optical of me looking at it and saying, oh, yeah, there's actually an object there. Mm-hmm. It's difficult for me to discern that, which makes me think that it's going to be difficult for the ML. Mm-hmm. There's also, you don't have a huge amount of data over time in the current approach that I'm using, because it's only optical flow between this frame and the previous frame. Mm-hmm. So we as humans can look at optical flow over a number of frames, mm-hmm. right? Which gives us, you say, oh, it looks like the path of a bird. But that's a little harder to discern.
Okay.
So in summary, it's probably worth a try. It's just not very high on my list of things to try.
Yeah. There are some other guys that I'm trying to make contact with, the two Indian guys who already worked on that particular issue to create a neural network that looks only at the physical parameters. So let's say how fast is something moving from frame to frame? How big mm-hmm. is it? Just outer shape geometry, let's say, without recognizing that is a bird, but just knowing that is an event of significance and it moves like this and that. And from the movement, then saying, looks like a bird, moves like a bird, let's say. Not looks like, moves like a bird.
Yeah.
Okay, I will make contact with Shivam and his colleague. Maybe they will jump back on board for that particular thing, for the physics, let's say. And yeah, anything else, guys? Otherwise, I would say it's 1.5 hours. If there are still things to discuss, please tell me. Otherwise, I would suggest we shut this down today.
All good, my side.
Yeah, it's all good. Thanks very much.
Okay, thank you, guys. Thanks for being on. I will stop the recording.